Okay. We shall continue with the phi bar of chart method, and for the sake of continuity, the solar load fraction is given by phi bar max y minus 0.015 exponential 3.85 f minus 1 times 1 minus exponential minus 0.15 x dashed times R s to the power 0.76. I shall quickly go through. R s is the ratio of the standard storage to the actual storage, and F is the solar load fraction. This correlation is an implicit relation, and you have got phi bar max, which combines the solar radiation statistics with the operating parameters yet to be evaluated, and all the collectors are in parallel. And it operates at a constant critical level. And lastly, this assumes an infinite heat exchanger and no tank losses. So, how to take care of the tank losses? How do we account for this? So, tank loss, something like UA of the tank times T tank minus some T surroundings. As far as this, I may call it QT loss. This is a load on the system. So, I shall change L to L plus Q tank loss. Okay. Then recalculate F with modified x dashed and y. So, the solar load fraction that you will be obtaining with this shall be, I will write it as F T L. This is actually can be written as, in the load I will have L plus Q tank loss, and in the numerator it will be Q useful going to the system. Okay. Then from this we shall calculate F solar, that is what is Q upon L, which can be algebraically calculated, and I am deliberately not giving the details here. The purpose will be best served through an example. The basic philosophy of accounting for the tank losses is consider the tank loss to be a load on the additional load on the system. So, the parameters x dash and y will change. Now, the solar load fraction calculated is inclusive of the tank losses, out of which we pick up the load that is going into, or rather whatever it is, minus Q tank loss. That will be the one that goes to the system. So, I can calculate what is Q s by L, right, but this is with a guessed T tank, right. So, this will correspond to some average utilizability. So, that will correspond to certain other T minimum. So, the collector will be having a input something like T tank plus T minimum by 2. So, you iterate until the difference becomes small to a 0.1 degree or 0.05 degree, whatever is the accuracy you require. Let me repeat, to take into account the tank losses, you assume a tank temperature. From the manufacturer specifications, calculate the loss from the tank, guess 1 with T tank minus T surroundings into UA tank, that is added to the load. So, now recalculate your x dashed and y and obtain the load fraction. That will be the load fraction where the energy is going to meet not only the system load, but also the tank losses. So, from that we need the solar load fraction. Corresponding to that load fraction FTL, you have a average utilizability. In other words, if I say that FTL is just like we have equated phi bar max, FTL is some phi bar average times y. So, this will be corresponding to average inlet temperature to the collector, which will produce this utilizability, and from there the real will be something like the minimum of the temperature T minimum and the T tank or the average temperature. So, again rerun it with a T minimum plus T average by 2 and see whether it is close to the initial guess or not. How do we take into heat exchanger? This also I shall only indicate if there is a heat exchanger. So, that T in to the heat exchanger will come out as T O to load. So, if this is to be at T minimum, ultimately collector will be operating at T minimum plus delta T. So, my collector operating temperature is T minimum plus delta T. So, this changes my X c, that changes my phi bar max. So, guess delta T, calculate solar load fraction, because your non-dimensional critical level has changed, utilizability has changed. So, F will change. If this is F multiplied by L, should be equal to epsilon L C minimum into delta T, correct. If this is the effectiveness of the heat exchanger multiplied by the specific heat minimum and a delta T available across the heat exchanger should be equal to the energy gain. So, from this I will get a delta T equal to epsilon L by FL by epsilon L C minimum, which is I will call it a 1 not equal to delta T, which we guessed. Recalculate with delta T 1 and end up with, let us say, delta T 2 and continue with this procedure until delta T 2 minus delta T 1 mod is less than 0.1 degree C or whatever accuracy you set up. So, basic philosophy is you include the tank losses as a part of the load, which will modify your x and y, and this strategy that will give you a solar load fraction as if the tank loss also is a part of the load, from which we can pick up what we call the solar load fraction, the amount of energy that is going to meet the load upon the total load. Subsequently, if you want to take into account the heat exchanger effect, you assume that the heat exchanger is responsible for operating the collector at a higher temperature T minimum, which modifies my X C bar minimum, phi bar maximum, and hence F. So, the amount of energy delivered is F into L, that should be supplied by the heat exchanger, which calls for a delta T dashed, which may in general be not equal to the guessed delta T. So, you iterate upon these two values come closer. We will do one example including the tank loss and the heat exchanger effect, then that should be even more clear. So, still withstanding the calculation procedure of the monthly average utilizability, first we reviewed the methods that are available to have long term performance prediction of solar energy thermal systems, and we realized long term performance is the indicator of the performance of the solar energy systems, because your meteorological cycle repeats itself in 1 year, and also economic analysis can be made. And next to system scale experiments, which are prohibitively expensive and time consuming, nevertheless, the importance is in identifying the system operating difficulties. Transys, and there are other popular simulation programs. These simulation programs also have some disadvantages. They need the skill of experts and large database, and the cost of the simulations could be quite significant if you are doing a small system scale simulation. And then to respond to standard systems, which may be 50%, 60% of the total number of systems, like domestic water heating, space heating, or service heating systems, or process industry requirements, the design methods such as F chart and phi bar F chart have been developed, and F chart supplies energy at or above 20 degrees C, which is based for the air based collectors as well as liquid based collectors, and phi bar F chart method can take into account the temperature at which energy delivery is desired, and that is given as an implicit relation in terms of another parameter in addition to the non-dimensional collector loss and non-dimensional absorbed energy, namely the monthly average daily utilizability. The monthly average daily utilizability is nothing but the solar radiation available to us above the critical level throughout the month, and that combines the statistics of the solar radiation as well as the operating conditions of the system. All these are applicable for standard system configurations. Now, we shall go to try to predict monthly average daily utilizability. So, definition we have understood, it is nothing but the solar radiation available to us above a critical level. Now, first let me consider 3 typical days in a month, just to bring out certain features I wanted, so that you will develop an understanding of what is utilizability and what sort of a function it is. This is the first set of 3 days, though they do not look identical, of say same radiation. Okay. 1, 2, 3. Later on, I will consider here a brighter day, a cloudy day, and sort of average day. So, this is second set, I will call it 1 dashed, 2 dashed and 3 dashed. Okay. So, 1, 2, 3 and 1 dashed, 2 dashed, 3 dashed have same h bar. Let us say the average radiation of all the both the sets 3 days typically, I just to illustrate the point, they have the same average, but one occurs more or less uniform solar radiation and the other one with a high radiation, a cloudy radiation and sort of an average radiation, right. And to further exaggerate it, so that I will make the scale bit less, you can see the point more clearly. Okay, it need not be continuous. So, now if you consider a 0 critical level here also, it does not require great mathematics, that my utilizability will be 1 if the critical level is 0 or whatever may be the distribution. Okay. This is anyway ratio, even if the numbers are different, averages are different, the monthly average daily utilizability 1 if I c is equal to 0. Now, if I reach this value, I t at noon of set 1, for this my phi bar is 0, whereas I c equal to I t noon, because they are all equal, that is the same value, phi bar is not equal to 0. These negative contributions do not contribute, okay. This does not subtract from this. So, I have this positive. So, looks like I can make a generalization, if you do not mind, non-uniform solar radiation from day to day basis will give a higher utilizability. For a given average, let us be very clear about it. Okay. So, if you have got a clearness index distribution which is more non-uniform, the standard deviation is more than another distribution, you will have a higher utilizability at particularly higher critical levels, because there will be at least one day that will be contributing to the useful energy, although the one with the uniform or more uniform solar radiation levels will contribute equally, of course, at low radiation levels, but at higher critical radiation levels the contribution will be less. Then when will it be 0 for a practical distribution, right? If you say that I c equal to I t noon of the average day, right, that means x c bar as we have defined equal to 1, phi bar is not 0, because there are days with I t greater than I t noon. So, one property is my monthly average daily utilizability, which is related to my x c bar, if x c bar is equal to 1 is not equal to 0. Now, phi bar, when will this be 0? So, we can have a quick estimate. If k t max is the maximum clearness index in a month of 30 days, 30 days or 31 days does not matter. Then if my IC equal to K T max multiplied by H 0, that will give me the horizontal radiation multiplied by R T at noon, that give me I at noon. Then again I can find out K T max into H 0 into H d by H will give me the diffuse radiation multiplied by R d noon. This shall give me I d, from which I will calculate I t noon on a day with excuse me, K T max. Okay. So, X C max for which phi bar is 0 is finite. So, approximately in fact you can, it will be approximately equal to 1 by K T bar. If average clearness index is equal to 0.5, if the non-dimensional critical radiation level is 2, almost phi bar will be 0. That is, if you assume that K T max can at best be maximum 1. So, the solar radiation at the noon time will be twice that of the solar radiation on the average day. So, the ratio of X bar should be 1 upon K T bar. It is a simple logic. You equate the noon time radiation based upon the average, what should it be, how many times it should be to be the noon time radiation on the day with the K T max. If K T max is 1 is this much, otherwise it will be K T max by K T bar ratio. But some approximations are involved. This is a finite number, one it will work as a ballpark value. You do not have to calculate utilizability beyond this value, but utilizability does go to 0 for a finite value of X bar. Just let me make it. So, this is the definition for the simple things. First, Klein has correlated the monthly average daily utilizability as exponential A plus B R n upon R bar. I wanted to write down the relation first and then let us examine how satisfactory, what are the parameters that have been taken care of. If you do not have the relation, I would expect my phi bar to be a function of obviously X c bar very strong, K T bar very strong, because K T bar will decide the sequence of the clearness indices or the cumulative frequency distribution, uniformity or non-uniformity of the clearness indices, as we have already demonstrated. A non-uniform distribution is likely to give us a higher utilizability than that of a uniform distribution, particularly at higher critical levels. And please understand, this automatically does not translate into higher useful energy. Phi bar max is high or phi bar max is low is different from phi bar max multiplied by H t is high or low. Okay. If you have a higher clearness index, the uniformity of the K T is satisfied. So, the non-dimensional utilizability may be lower, but the actual energy gain may be more, but less proportional than the increase in the K T. So, when we talk in general solar energy or heat transfer, if we talk about a non-dimensional number, let us talk just non-dimensional number, increases or decreases, or rather than mixing up with the real physical variable. These two may not be synonymous or equivalent to each other all the time. And x t bar, k t bar, and the latitude, because it will have some effect definitely on what will be the noontime radiation compared to horizontal radiation, or the tilted radiation compared to the horizontal radiation. The slope, delta, declination the month, because my this R B R factor strongly depend upon this, and of course, gamma if it is non-surfacing. So, Clearness correlation is has f x c bar, k t bar is there, this comes through A, B, C. Of course, he has chosen gamma equal to 0, and instead of R n upon R bar is in place of phi beta delta. So, this is R n is the noontime tilt factor to a daily tilt factor. Okay. Basically, it is very difficult to show only in one picture, but you can understand the spirit of it. If this is the horizontal radiation, a particular orientation may make a steep radiation at the noon time, and another distribution may make it larger throughout. Here R bar may be large and then R n not so large. Here R n is very large, R bar may not be so large. So, what he is trying to say is the effect of the phi beta along with the month will stretch to a larger extent or to a lesser extent, though it may overall increase the total solar radiation or decrease the solar radiation depending upon the length of the day, etc. For example, with the few examples we have calculated, R B factors in general for favorably oriented surfaces towards south or higher in winter, that means R B n will be higher in winter than R B n correspondingly in summer. Okay. So, this is so he expects rather the correlation very successfully phi beta delta, which are 3 parameters, are combined into a single parameter R n by R bar. The logic behind that is you will know how much the stretching took place to overall inflation, you call it, or increase of the solar radiation. However, if you go through little detailed calculation, not always, I am not trying to say this correlation does not work, it works well. And if you choose phi 1 beta 1 delta 1 and phi 2 beta 2 delta 2 such that R n by R bar 1 equal to R n by R bar 2. This is possible, because I have got 3 variables phi beta 1 delta 1, this arbitrarily I will choose, find out R n by R bar, assuming assume a particular phi 2 beta 2 or phi 2 delta 2 is not in my hands, find out a beta such that these 2 variables are equal. So, 2 of them are free. So, consequently, 2 of them can be fixed such that this ratio is equal to this. So, if you examine a large number of sets of phi 1 beta 1 delta 1 and in general phi n beta 2 and R n by R bar is differs for different phi beta deltas. This is obvious, but even if R n by R bar is the same, is utilizability same? So, according to that correlation, for a given k t bar, of course, and x bar, they are the same, right, but they will not be the same, or they will be the same, which we have to find out from the data. So, such studies we have done. Under certain conditions, the utilizability can be different, even if R n by R bar is the same for two different sets of phi beta delta. Of course, you have to really search the combination, because your k t should be the same, x c bar should be the same, etcetera, etcetera. But nevertheless, in general, if this is established, you may have a method to get my phi bar in general valid for x c bar, k t bar, phi beta delta gamma. So, this is the complete picture, even if you take non south facing surfaces into account. For example, Klein's correlation is valid for flat plate collectors, and Collares, Pereira and Raubel they developed correlations for concentrating or focusing collectors. Good for phi utilizability greater than 0.4, that means for higher utilizability. So, generally some approximations have been made. The argument has been concentrating collectors, unless they operate at a high utilizability, the efficacy cannot be felt or cannot be realized. So, any relation for phi bar above 0.4 is good enough. Of course, there are other limitations, but that we shall not go in this course. So, the constants A, B and C very correctly, it is a function of clearness index, and B is minus 4.345 plus 8.853 minus 3.602 k t bar square, and the constant C minus 170 minus 0.306 r, there should be a k t bar plus 2.936 k t bar squared. So, this is a nice relation. You have got utilizability in terms of x c bar, A, B, C constants which take into account the clearness index, and one factor to represent phi beta delta, which works reasonably quite satisfactorily. And that R n, the noon time tilt factor, which I shall again remember recall, can be written as, because it is written in terms of those quantities that we know and which we would not like to use the hour by hour data, since this being a monthly design method. RDN, sorry, 1 plus cos beta by 2 plus ground reflectivity times 1 minus cos beta by 2. You remember in our long form or whatever, in the terms of the data values, it is 1 minus I d by I times R b in general plus I d by I times 1 plus cos beta by 2 plus rho times 1 minus cos beta by 2. Okay. Now, noon time this n comes into that because it is at a particular time. Now, you will see that R d n by R t n is I d by I, this is I d by H d multiplied by H d is I d, this is I by H multiplied by H is I. So, this is nothing but I d by I. So, is here I d by I and this contains nothing. Okay. So, what we try to do is express in terms of the diffuse fraction and the R t and R d correlations to estimate the solar radiation at the noon time. This is done on the average day of the month. You recall in the definition of the non-dimensional critical level I t n R n in the denominator, we need the noon time radiation on the average day. To calculate that you need R n. R n is given by this expressed in terms of R t and R d, and H d by H is calculated as a daily diffuse fraction. Though it is the average day of the month at k t numerically equal to k t bar. So, we know that we are making the calculation on the monthly average day, but the diffuse fraction for some reason or the other is calculated with a clearness index numerically equal to the monthly average daily clearness index. The possible reason could be a single day when the critical level reaches the noon time acts like, though it is an average day, acts like a single day possibly. This is a logic I am trying to give, and hence H d by H is calculated with k t numerically equal to k t bar instead of a H d bar by H bar, or this simply correlates better and hence this is used. So, once again yes, this phi bar does not go to 0 for large x c bar. So, since this being a exponential relation, this shall not go to 0 for high values of x c r, even x c bar tends to infinity. So, if you want to have certain limitations, first of all concentrating collectors satisfactory utilizability method needs to be found, then for non-south facing surfaces needs to be found, and whether R n by R bar adequately represents phi beta delta needs to be done, and it will be nice if phi bar goes to 0 at some finite x c bar, since we know that, and so somehow these desired properties of the utilizability function to be satisfied, and there is what is meant by equivalent day method, that is EMD. This is done at IIT Kharagpur, India. So, now if we ask ourselves a question, why can't we follow the methodology like estimating the solar radiation, that is say for example, R times H t summation over all the days equal to, or you call it double bar, what, it does not matter, H t bar. One average day solar radiation, you take it multiplied by and find out the tilted radiation. I will sorry, this should be not T's, sigma R bar H I over days should be equal to or. So, one single day calculation, this is within 3 to 4% or 5% difference, and there is no apart from a numerical difference, there is no qualitative error in this type of a calculation. This works for RB, works for RB bar day, RB bar month, and in general R bar, and in fact even for the tau alpha bar for the day, average days value will be the monthly average value pretty closely. Why not for the utilizability? That is because if I c equal to I t bar noon, x c bar is equal to 1, and based on average day only, my utilizability will be 0. So, like the 3 diagrams I am showing, if you base it on this is the average day, this is x c bar is equal to 1. If I calculate only on based upon this, then phi bar equal to 0, which is not true, because I have got a positive energy contribution on the day with a higher k T. So, this is the reason all the days do not contribute to useful energy whenever the solar radiation highest available is less than the critical level. Still the average day would have worked if I had taken these negative things into account, but negative things are not given a penalty, right. This is treated as 0, I t minus I c plus only summed up. So, this has to be taken into account, but not this deficit. So, the average day does not work. So, if you realize that the average concept, why it fails for calculating the monthly average daily utilizability, because basically you do not take into account the negative contribution. Whereas, in the case of calculating R bar or tau alpha bar, a day with a higher k T may have a less value or higher value to be compensated with a day with a lower k T or a higher k T. That does not happen here. So, what we can do is, if we have cumulative frequency distribution like this, that we know from Leon Jordan. This is, let us say, at k T bar is equal to 0.6. Okay. So, x c bar is some value 0.72. So, this corresponds to certain I t noon. This corresponds to certain h t and h and k T. Okay. I have calculated for a system based upon the solar average radiation, which x c bar turned out to be 0.72. I can calculate from the correlation, all right, but just if we want to do some other averaging technique, I will just say that this corresponds to the I t noon 0.72 multiplied by whatever is the f r u l divided by, I will get the noon time solar radiation, from which I can get the tilted radiation and or the horizontal radiation and the clearness index. So, that clearness index, so I can say this one is sort of a k T min corresponding to my x c bar min, and this many days will have a k T greater than k T min, or this much of fractional time will have the clearness indices hourly basis or daily basis higher than the noon time radiation when it is just equal to my x c bar number. So, these things I will call it NC the number of contributing days. Let me just repeat, because the concept is little tricky. If you have got a certain non-dimensional critical level based upon the conventional definition, that will correspond to a particular IT noon, and hence on the average day KT bar is known to me. I can find out what is the critical level corresponding clearness index to that XC bar. So, as long as the critical clearness index is higher than this minimum clearness index, all these things my IT minus IC is greater than or equal to 0. This will be 0 and here onwards it will be positive. Okay. So, now these days need not occur. This is not day number 1 of the month and this is not day number 31 of the month. Okay. Sequence can be anything, but there are certain NC number of days for which my solar clearness index is higher than the minimum clearness index that will meet the critical level that we have decided. Okay. So, now find average of KTs of the NC days. So, what is the clearness index average for the days for which the KT is greater than KT minimum? This, for sake of some notation, we will call it KT star. Okay. So, now this is, I will define this as the equivalent mean day. So, now I have got only one day with a particular KT bar star. So, this is the distribution, this is my IC, this is the energy gain on the average day. So, if NC is the number of contributing days and I have got HT star as the radiation on the tilted surface on the day with a KT star or KT star, sorry, this multiplied by phi EMD. Somehow I calculate for a single day's equivalent or mean day utilizability, that multiplied by the solar radiation multiplied by the number of contributing days is the energy contributed, right. So, this should be equal to all the days times HT bar multiplied by phi bar. This is my conventional definition, which when multiplies the total radiation on the surface will give me the radiation above the critical level. What I was trying to say here is, if for this equivalent mean day, if the single day's EMD is this, that multiplied by the solar radiation on the equivalent mean day, that multiplied by the contributing number of days, because the other ones are 0, the energy coming from these things should be equal to the total energy based upon the monthly average daily utilizability from the conventional definition. So, now my phi EMD will be n by, sorry, what I want is phi bar. So, phi bar will be NC by N times HT star by HT bar or times phi EMD. phi bar is equal to phi EMD, that is it. NC is known, for that I need the Leon-Jordan clearness index distributions, then Hg star into Hd bar. So, this can be simplified further, NC by N times you have got Kt bar star H0 bar into R bar star upon Kt bar H0 bar, that remains the same more or less, times R bar times phi E m d. So, this shall be equal to N c by N times Kt bar star R bar star by Kt bar R bar phi E m d. So, I can calculate the monthly average daily utilizability. If I can somehow calculate the single day's utilizability, that single day being the equivalent mean day, which we have defined as the day having a clearness index of average of the days with the critical level higher than the lower than the noontime radiation of n c number of days in the month. We shall continue with this in the next class. Thank you.